Narinesingh lectures at the University of the West Indies in Augustine in the Department of Civil and Environmental Engineering. So I'd like to call Engineer Narinesingh to the podium, please.
Well, good afternoon, and I have my director here with me to help with any problems. I did spend 10 years in drainage division. I enjoyed it so much that I went on to do river engineering and fluvial geomorphology, and I'm pretty much concerned and excited about what goes on. So my talk, fluvial geomorphology in river maintenance. So I'm going to present the issues in river maintenance with respect to debris. As you see, that's a main problem causing flooding. Riverbed scour and erosion, the inadequacy of hydraulic design considerations. Then I will introduce a topic which you're not so familiar with. It's fluvial geomorphology, and it's about the natural processes of sediment transport. We have issues with everywhere there is desilting exercises taking place, embankments going up without the design for an embankment. A case study of poor drainage construction practice in the farm road area, Valsay. And then maybe we have some opportunity for questions, and I will hopefully get help from my director. So the issues. This is an intake for the agricultural station in St. Augustine. It's blocked with debris, as you can see here, bamboo, industrial household waste, This is an outfall. An outfall is usually a small stream meeting a larger stream. Now, the construction work is not adequate because there should be scour protection and bank erosion protection. That apparently was not there. So the structure interacts with the floods and you have scouring. This is in Mount Dore, a sill trap which has lost its screens, again because debris accumulated, blocked the waterway area, the flood level rose, the hydrostatic pressure forced the screen, we lost it. Issue with proper management of the paved area. This should have been not sloping but horizontal. That increased the energy of the flood or the water coming over this weir, and it caused about a 0.5 meter scoring. So while you're trying to hold the sediment back here, you are providing the sediment there. Scours at bridges. If you look down I'm looking down from here taking this picture. This mass concrete was placed to protect the abutments. So scouring occurring as flood goes through the waterway area. Mass concrete poured to prevent the scour or to stop the scouring and to protect the abutments. But then the scour just moves downstream. So the scour moves forward. You have the retaining walls collapsing, bank erosion, and this nice green pool here, that's a scour hole. It extends, I did not measure this, but this is the extent of it. You have the collapsed retaining wall. This is the scoured sediment accumulating there. Now what happens next? Drainage wants to remove this buildup of sediment, so a contractor goes. I'm not sure if he gets enough supervision, but he would remove this that he sees above the water level, and then he gauges this depth and decides, well, I need to get some of the water up. So he goes down further. So this is already scoured. So you've lost about a meter, and when he removes this to get that water out, he's actually removing the bed level, increasing the bank heights, and well, the bank will be threatened with the next flood, and you'll have further scouring. So not only in the lowlands, but in the steep slopes. This is in Degomartin, 17 August 2012, maybe you remember that event. This is probably a paved channel by private personnel, because I am sure Drainage Division will not, I'm sure they will not have such thin slabs. So poor workmanship, probably not supervised by Drainage Division, got scoured, broken. I think undersized culvert here is hidden by the accumulation of sediment. The flood level rose, and that road being steep, when the flood level rose, the cars parked on the roadside went sailing down the road. So now, how is fluvial geomorphology going to help us with this problem? Well, first we could identify the problem. Fluvial geomorphology embraces the continuity of flow and sediment from the hilltop to the coast and wetlands, to the wetlands. So it's the entire system. It's an understanding of the processes of water and sediment movement, water and sediment movement over land, in rivers, and in their floodplains. Now, to get the water, we need the hydraulic cycle. So the hydrologic cycle, the sediment movement is in a response to the hydrologic cycle. And to review what that is: evaporation at the surface, condensation, precipitation, and runoff. Now you're on the steep slopes of the hill, so weathered material will be easily transported. There's a lot of water energy. So it transports volumetrically a lot of sediment and also large sizes. However, when it encounters low slopes or pools, you will have sedimentation occurring, and the sediment moves with the flow, and when it reaches the coast, you then get beaches and wetlands being formed. Wetlands are extremely important, but they cannot exist without sediment being supplied by the rivers. So the Karani swamp, the Oropouche, Naribadi swamps must have their sediment supply. So if my director captures all the sediment upstream, we will lose our swamps. So we have to make sure we allow some sediment out. Now, what else the wetland does for us? It stores sediment, it creates new land, stores pollutants, makes it safe, absorbs floodwaters and storm surges, habitat for wildlife, and nursery for fish. So it's very important for other industries. The story of sediment. So with overland flow, you get fine sediments coming into the channel. The valley slopes or the banks produce the larger size particles. If you take a section through the mountain, the hill, and to the river, primarily you get erosion here, but in the movement of the sediment, there's also some storage, then storage in ponds, storage in the lowlands, storage in the banks, and in the channel itself. These numbers tell how long it takes to remobilize those sediment. Hundreds to 1,000 years, hundreds to 1,000 years for the riverbanks. You will get that superficial layer moving probably on an annual basis, but it's also hundreds of years. So can we get rid of sediment? No. We need sediment. Yes. This is a tributary in the northern range. Notice the variety of particle sizes. You need a variety of floods, and that will explain the storage period. So we have a sediment budget to work with. From the hilltops, you have sheet erosion providing this width indicate relative amount of sediment. So you get gullying and tributary contributions. We add these up, we get this contribution here, that relative magnitude. Storage in the uplands, in the tributaries, and the upper main valleys. So this is the supply, this is the storage, and then the lower areas, or Carney Plains if you want, stores most of it. What ends up actually in the sea is this very small percent. So it's moving very slowly through the system. This is a in the St. Joseph River near the foothills. So this is drainage engineering assistant from long time ago. So he's about 5'5". This is the channel width, and you have large volumes of storage. And that's in feet, so how much is that in meters? Less than 2 meters. Right. So summarizing for the sediment transport. Steep hills, a lot of energy for the water to carry the sediment, a lot of sediment generation. Lower slopes, sediment deposition to some extent, reduced erosion, but it more acts as a transfer zone, and then the Carney Plains is the storage area. Moving on to the exercise of desilting and embankments. The blue area is the main channel, is what the common person would look and say, that's the river. But the river includes the floodplain. A section through here will look like this. This would be your river section. This is your base flow, your dry season flow. Your 2-year, well, it's a range between 1.5 to 3-year return period flood will demark your bank full flow. Typically, that edge is also shown as the permanent vegetation line, so you can identify it in those ways. So the rest of this gentle slope here, you can have a 10-year or 25-year return period flood, and that will identify your hydraulic floodplain, depending on the frequency. The wetland situation. You have channels within the wetlands. You can have a low tide, it may be dry, or there may be some water. Then a high tide, which will flood the wetland area, obviously. And if you have a flood on land, at the same time you have your, well, when I say flood, a heavy rainfall event occurring at the same time you have high tide, then there's slight change in the depth of flow over the wetlands as the flood water gets into the wetland area without impedance. We need land, we like the floodplain areas, so if we were to build an embankment at the edge of the river, on the bank itself, as indicated here, the 2-year flood frequency, if we build that, then there is no access for the flood, no storage area. So we build in these areas, we build up these embankments. The flood water that would have been there now has an increased elevation. So the 1 in 25 would have been here before the embankment is now here. And if the embankment is not high enough for the particular flood return period, you will have disaster occurring where you expect it to be dry. In the case of the wetlands. So similarly, if you were to build embankments, you confine the flood, not the tide, because the tide has a fixed level, but flood events coming on top of the tide will have an increased elevation. Now, we are not just causing flooding by doing this. What we are doing in the wetlands, we are actually changing the habitat. The vegetation changes, and then species that we have not identified might be disappearing. So whenever we tamper with the wetlands, we are causing problems that we are not aware. So to summarize, if this is a channel bed, the base flow and the 2-year flood return period are not interfered with, although we do sometimes fill in that river section and build retaining walls, reducing the capacity even at the 2-year return period. So let's assume we don't do that. So we have the 25-year flood here actually being higher in the embanked area. We have backwater effect here causing flooding upstream likely, and then the floodwaters have to go through quickly through the embanked area, so you aggravate flooding downstream and possible erosion. And this is where it's happening. These are real pictures, not drawings by me anymore. Real pictures. St. Augustine South. So I went to UE in the 80s. I know when here used to be flooded. When there was a flood, it would absorb the floodwaters. The channels have been cleared, regular maintenance. They're now taking the floodwaters out. In doing so, embankments are being built because the operation is we take it out here, we drop it there. And if we build up these embankments, there's no more flooding, there's no more absorption of the floods in that area. And you'll see in the next slide further problems. In St. Augustine, this is the law school, this is the transformer room, you have a secondary school here. The silt in here, the material sometimes will be taken out, but again, sometimes it's just piled up on the edge here. It does actually prevent floodwaters from getting into the schools, which is a very good thing. But this year, the Eastern Main Road had 1 meter of floodwaters because the water came down in greater volumes because there was no capacity, no space to store the floodwaters. So this is an example of similarly removing material and putting it on the side of a drain that is going through the Caroni wetlands in the Beetham area. I have the Caroni River embankments here to indicate that if we design it for a purpose and it serves a purpose, then we should be happy about it. But if there is no design and things are happening without our intention, then we should be concerned. And the concern is this. This is the St. Augustine South, and that embankment is built there, and the guy is now happy to fill his land. He isn't getting flooded anymore. And warehousing we're talking about, much more warehousing. The way, the shape of the land and then filling, I expect it to be something like warehousing or a factory. This is desilting of, I got this off the drainage website. I'm not sure which wetlands this is, which one it is. Director, you know?
The top one is the East River, the bottom, I'm not sure.
So the desilting is going on and the material is being accumulated there. And obviously over time you'll have an embankment built over quite some extensive reach. And what is going to happen with the habitat there? I don't have the answer. The cost of river works. It is not cheap. We are spending a lot of money. 62 bridges, $404 million to 2012 at 2010 estimates. So it's probably much more than that. I'm not sure how the contract is going out. $30 million for studies. $8,000 per meter for a box drain, $450 million for part of this water spilling flood alleviation project. This I got off the NETCO website. Case study of the St. Joseph River Wear, that is the Balsane agricultural station losing its water supply. So this is Port of Spain, this is the St. Joseph River catchment. This is from Google Maps, a 3D showing that the simplest place for us is within the flow path of the river, which is in the valley, the bottom of the valley, that's where we build. In the foothills and in the floodplains. So we have to build, but we have to work with the water, with the river. So you've heard about the EMR, the Eastern Main Road. This is the St. Joseph River here, the priority bus route. This white is concrete paving of the bed to protect the abutments of those bridges and to retain the banks, to prevent erosion. This is the location of the weir, and this is some bridge construction works, and the story begins. In a few minutes to end. I did this refurbishment of this weir 1997 when I was at Drainage Division, so I'm familiar with it. And this is 2003 Google Maps showing the broad section of the weir, the gated section there, and works in progress. A previous bridge on this road collapsed here, and the contractor diverted the stream, the river. What happened in the meantime over the years is that downstream here, dredging works or desilting works continued, and the riverbed was lowered by a meter or more. So by diverting the river past the collapsed structure, you had this increased gradient, and flood events then, now experiencing the steep gradient, caused the erosion of the bank and the loss of the water supply. And this is 2005, and the bridge works is continuing. This was the apron of the weir in 1997. This is the top of the apron, and this you will see is the present bed level. Now this is the old days where you took a picture and you went and you printed, right? So, construction work, the broad section, and this work was done by Drainage Division workers. So the concrete paving there, this is the finished product. This year, these are slabs of stones to dissipate the energy so you don't cause erosion downstream of the weir. This rough surface is now 1.3 meters above the riverbed. So this could have been avoided. What the farm has to do as a result of losing the weir is drill a groundwater well and cost for electricity and pumping and all the continuous cost that goes with that exercise. And so, this is 2003, the weir was there, the bridge under construction. 2006, the road is in place, the bridge is there, massive concrete works to protect the poor alignment. And this is what was, this is the finished product. 90-degree bend, large concrete, sediment accumulation, vegetation, erosion continuing, 90-degree bend, 21 meters cover, and about 1.2 meters depth, cover depth. If that is not bad enough, 400 meters upstream is a priority bus route. That gradient in 2010 gave the flood so much energy that it eroded 3 meters of bank. The electricity pole fell in, and this car eventually fell in. So just building that bridge, it's not a matter of going there and pouring some concrete and putting a slab. You're dealing with the river, you need to look at the geomorphology and the hydraulics. So in conclusion, given the cost and importance of structures, you need the appropriately trained and experienced, what do I have there, engineering and environmental professionals to play a greater role in this whole hydraulic studies and implementation and maintenance, etc. And any questions? I have my director here.
Thank you, Engineer Narinesingh. We just have a few more minutes for questions. Maybe just 2 questions. Anybody?
Hello, good day. Jason Watty from National Gas Company. I want to ask the last speaker about the term box drain, and how does that affect in this new world that we live in? How does it affect hydraulics in communities as they become more prevalent?
You're opening up a really large can of worms.
You have 2 minutes to do it.
Okay. Box drains, do have its purpose and function. The way it is being implemented now is wrong. There are standard designs, meaning that there's a standard section that's being applied just about any and everywhere. It appears contractors with now, I'm guessing here, well, they have to train the personnel to implement it, but I've seen drains going in the wrong direction. They try to send water up the hill without a pump. To be short, the implementation right now, I don't agree with. My director could add anything if you want.
I think Engineer Easterman might talk about that during his presentation. Am I right in saying that? Yes, so we will.
But I just
want to be full answer.
Because it's connected to another engineering problem, as you say. You see, when these things look like this, yes, they cause problems with drainage, and the National Gas Company now, because of all this change in dynamics, it causes us a problem because we have more landslips in areas that we didn't have landslips. So it means that it alters the pipeline and it exposes certain areas of the pipeline. And even in our engineering departments now, we have to foresee that engineering design. So yes, river morphology causes problems, I'd like to highlight with water going down, but it also causes further complex problems in other engineering industrial areas.
So the obvious question is the coordination, right? And I don't know to what extent that is happening. Maybe we can, hopefully we'll have some time at the end of the session so we can perhaps address that question. The issue of coordination and how in fact we can move towards forming something that is comprehensive in nature. Okay.